So today we're going to be going over reinforcement learning. This is a really cool topic because I think it's very relevant, and I have some cool videos I put in here to see. So just a quick recap. Last week we went over MDPs and MRPs. So we're building off of what we did last week about MRPs. We talked about like, the rewards and stuff. We touched on the idea of policy. Today we're going to be building on top of that. So real quick, Markov chains and NDPs, you have the main thing is that if you condition on the current state, the past and future are independent. You guys remember the Markov property and everything. Um, like the main thing to remember from last week is that we talked about how if you want to know what's going to happen in the future, the only thing that depends on is like what you did yesterday or what your current state is. That's all you need to know. That's the main idea to remember. And for rewards, that each state has a certain reward attached to it for Markov decision processes. And at each state you're in, you have to make some sort of action. All probabilities at a certain state add up to one. That's all the main idea. M is how we talk about number of states. S is states, T and P are the transition matrix. Same stuff we talked about last week. Um, this agenda is not accurate. So I did these slides yesterday night, and I did some of them over the weekend. So this agenda is not fully accurate. We're gonna do this later. Yeah. Anyway, this is good. So my first question for you guys is, what does reinforcement learning mean to you? When you think of the idea of reinforcement learning, what do you think of?
Learning through reinforcement. AI getting better at the things it's already good at.
Yeah. What are some examples of places where reinforcement learning is used?
Video games.
Video games, yes. Yeah, that's a really big one. There's a lot of different ways that it's used. It's used like in video games. There's like the chess bots that do reinforcement learning. Um, RL is a really big thing in robotics as well. You know, for different movements, like what's it, Boston Dynamics. Um, it, I think if you really think about it, babies are basically kind of like robots. Um, a baby when it's being raised is kind of like a reinforcement learning problem. It's That's going to be a big example because I think it's a great problem. Honestly, it's a great way to think of like a little baby and the way it interacts with its environment as like an agent interacting with its environment. I think it's a great example. Certain controllers also use reinforcement learning for doing certain like spacecraft maneuvers. But here's the main question that I have for you guys. How is reinforcement learning different from supervised learning?
Um, I wasn't here last week because I had a quiz, so um,
It's okay. It's just like a general question. We didn't talk about the last week. But if you think like from what you know about supervised learning, right? How does a model get better with supervised learning?
It has information that it already knows, and then it compares the predictions it makes to compared to that specific known data. Whereas with reinforcement learning, it's trying to do certain actions or get to a certain endpoint that'll give it either like a reward or some kind of detriment to itself.
Yeah, there's no direct supervision for reinforcement learning. There is not a yes or no. The only thing that's sort of guiding the model are rewards. Think of another thing about how supervised learning, what does the data look like?
Features and labels.
yeah.
Features and labels. How does it look like from reinforcement learning?
Believe,
It's not features and labels.
yeah, honestly,
Is
like
you're not going to have that in RL if you're training. The other thing is the actions that you take as a model in reinforcement learning affects the data that you get after. When you make a decision, the next state you can go to, it changes. It's not always the same. So that's I'm just trying to sort of separate the concept of reinforcement learning a little bit from supervised learning in this way. So in reinforcement learning, we have two different sort of things at play. The first is the agent. The agent has sort of three main things that it does. It decides on an action. We'll call it AT. And after it decides on an action that it gives to the environment executes the action, computes the next observation. So let's say that you're a baby and you want to crawl around. And so you decide on an action to sort of roll. The environment will execute this rolling and compute the next observation we'll call O of t, which could be now you're on top of a carpet. After computing the next observation, it'll send that back to the agent. So it'll go like this way. Observation goes back. And now the agent has the next observation and gets the next reward. So by rolling, now this baby's at a new location. What is the reward of that location? Is it trying to reach some sort of food? Is it trying to reach some sort of toy? What is the reward attached to that location? And so when I say agent, I'm talking about the model and the way it interacts with its environment, which is where the model is sort of being executed within. Does this vocabulary make sense?
Makes sense.
Okay. So what is a reward? We touched upon this last week, so I'm just going to review it real quick. A reward is something that may be positive or negative. For example, if this baby is trying to get, let's see, why is this not there? If this is where it's like a region of where it's going to be. So where it is, it's trying to get here to some toy. Maybe there's some sort of hazard here. It's trying to get here. And it can have multiple actions of trying to walk, which can cause it to fall, or just crawling. There are multiple different rewards. What can happen if the baby comes over here? There's a certain reward attached to it. Here is a certain reward. If this is like your final destination, this could be plus 10. Going here could be plus 1. Here could be plus 1. And maybe going backwards is minus 1 because you're going away from the reward. The reward can be positive or negative. There is nothing about why in this reward. There's not like, why am I getting this reward? But this reward is related to the action that you just took. What our goal is we want to maximize the total reward that we get. For example, the baby, we want to move. We can roll, crawl, walk. That can all be positive. Right? These are positive actions we can take. Falling, on the other hand, is negative. Or, for example, with if you have a model that's supposed to handle your stocks, earning money would be positive. Losing it is negative. Does that make sense?
It makes sense.
Okay.
Doesn't for RL, it kind of assumes that you already have knowledge about whatever environment you're dealing with, so it can only be used in a situation where you kind of understand what you want and what actions are beneficial towards it and negative towards it.
Yeah, exactly. It's about how are you going to interact with your environment? What actions are you going to take that'll either help or hurt you towards getting to your final goal? So the main thing is that actions have consequences, and depending on actions you take, rewards may be delayed. For example, as a baby, we could keep crawling to reach destinations forever, and we'll always have some positive reward attached to that because we're still moving. However, we can keep taking the same exact action of continuously crawling, and if we keep doing that, we will reach our destination, but we may never learn to walk, and walking may have a greater reward. Sometimes we need to sacrifice immediate rewards for long-term benefits. For example, if you try to walk, you might end up falling down. But if you keep falling down enough times, eventually you'll be able to learn how to walk, which has a higher reward later on. Sort of like this is like you want to rob a bank because you really want a bunch of money. If you rob a bank, you're gonna go to jail. If you don't rob a bank, you might not get that immediate reward of a bunch of money, but you avoid going to jail and you can get a job instead and make money eventually. So the main thing I'm trying to get at here is, as your model's like main purpose and goal is like, how far ahead are you able to plan to get the highest reward? Does that make sense to everyone?
Mhm.
So this brings me to a question for all of you. How do you make decisions? What do you base them upon? For example, if I had asked you, what time should you, that's not even a question. What time should you go to the dining hall? What would you tell me? If you don't want a long line, how do you know that that's the best time to go to the dining hall?
Either go early or late
Yeah. So how do you know that? What do you base your decision upon that? Oh, I should go either early or late.
based on,
Because we've gone there when it's not early or late, and there was a gigantic line.
Yeah. It's based on what you've done in the past. It's what you've observed about the lines at the dining hall. So it's like you make your decisions based on what you've seen before. So similarly, in reinforcement learning, the decisions that you make is sequential. The environment gives us rules that tell us what we see and what rewards we get. But it is up to us ultimately, how should we use observations that we know to make decisions? For example, if you're deciding when to go to the dining hall, should I use just my observation of what I saw at the dining hall yesterday? Should I use my last two observations, my last three observations? How many of these should I use such that it's able to benefit me adequately on making my next decision? And so this idea here is how we get to the idea of the agent's policy, which we talked about a little bit last week. The idea of the policy is it maps where we are now to a certain action. For example, if we're currently doom scrolling on our phone, an action could be, let's just put the phone down and let's lock in. That could be a policy. If we are locking in, continue locking in, don't pick up the phone. That could be a policy. The idea of policy is sort of this sequential idea that you can take either just, if I'm at this state, always take this action, or you can do the idea we talked about earlier, where you use your previous observations to make decisions, saying that given that I'm at this state and maybe my previous state, what action should I take? Or given that I'm at the state in which observation I have, what action should I take? That's sort of the idea of policy here. Now, I have some videos of reinforcement learning, which is interesting to see about how this idea of policy improves over time. See if this link works. Can you guys see?
Yeah.
Okay. So this is Boston Dynamics. They have this little robot, and they're showing how it learns like to walk using reinforcement learning. So it's like, how is this robot developing like a policy that, given it's in some sort of state, what action it should take to be able to reach its goal, which is walking? So you can see here, it's like over time, it's able to develop a better and better policy of knowing that, like, if it's upside down, the action it should take is like trying to like flip over using its other two legs. And now that it's up, what should it do now to learn how to walk? This part's kind of sad. It's like it looks like a dog. It's like like oh, poor robot. But it's really interesting to see that how it's able to get a lot better with time. Yeah, I thought that was a really neat video. I forgot which one I have as the second one, but I think if you have time at the end, we can go back to it because I know I did start late. Um, okay, let's go on to the next one. Let's exit that. So now let's just do a quick review of Markov reward processes. So if you guys remember, the main thing about MRPs is that you have multiple states, you have multiple actions that you can do, you have probabilities, which are these. These are our rewards here. And this probability distribution is our transition model. We got our rewards, and then there's our policy that's what we want to develop. There's the idea of return, which is the total discounted reward we get from at a certain time step t, and then there's the discount factor. So just as a quick review, as you remember, at each one of these states, there is a certain reward you get, which is like the expected value of being at that state. The discount factor is that depending on how much higher you make it, it's do we care about getting getting a higher reward immediately, or do we want to care about getting a higher reward over time? So if you have it really close to zero, we care about getting rewards immediately. So for example, in this case, it would mean that let's just quickly reach our, so in the case of like, say, rotting versus locking in, if our goal is to lock in, or where's that example? In this example over here, if our goal is to pass the class, should be R equal to plus 10, then a myopic reward would be, okay, let's just immediately go to day drink because that has a higher reward and we can quickly reach this goal here doing that. Versus if we cared more about a more like balanced thing, if we had like positives here and here, then maybe you'd want to take like the class and discussion route to get to pass the class. So that's just the main ideas of myopic versus far side of evaluation for the discount factor. Is do we care about getting rewards quickly, or do we care about getting rewards in the future more? So, so one of the main questions that you'd probably come up with is, what is the value of getting to a certain state S? And this and calculating this is called like the state value function. So it's basically saying like how well are we doing at this point in time? The state value function tells us g of t, which is the return, the total return that we get given that we're at a certain state S. So if we want to go to the rotting state, it would be what's the gain? What is the average value of rotting given that we're currently at, I don't know, like go to class or something if there was an arrow pointing towards that. The main thing about this idea here is that it's able to play into figuring out like when we want to get to our final goal of pass the class, we want to find out the best sequence of states that we should go to so that we get the total reward such that the next state that we're going to is like better or it's worth it. Is it worth it to go rot? Is it worth it to go to discussion for our final goal? And this all ties in heavily with our discount value because depending on whether we want this reward quickly or if we want it later, that affects what decisions we make. So now the next thing that we're going to go on to doing is using this equation here. So this equation here is recursive because the next state that you go to is dependent on your previous state. And that's the same thing that we talked about earlier with like the with Markov processes, that everything is dependent on where you were before. So let's go here. So let's say that we have a discount factor of 0. Let's connect this line here. So we have a discount factor of 0. And what we want to know is what's the value of each one of these states. If our discount value is 0, remember, what does that mean? What do we care about? Immediate reward or later far-sighted rewards?
I'm not sure.
If our discount value is 0, all we care about is getting a immediate reward. What we care about is in like one iteration of this state value equation, where can we get to? So if that's all we care about and we're using this equation here, our value at this state is just equal to our reward. So our value of rotting is just -1. For class, it's just -2. Discussion, -2. Passing is just 10. Day drinking is 1, and sleeping is 0. So this idea is that if we care about, this is going to be like our like first iteration of having no discount. So it's just, if we just want to get a reward fast, we want to get it quickly, the best state to get to and the state with the highest value would be day drinking, because that's the only positive reward here. Does that idea make sense to everyone?
Yeah.
Okay. Then let's go on to if our discount value is a half. That's just the answer. So if our discount value is 0.5, then the way that we're gonna go about this is that we start with just our initialization. So when I say initialization, basically what I'm saying is that we start by setting the value of every state to 0, and then we repeatedly apply that equation I just went over, where each state's new value is its immediate reward plus the discounted sum of its neighboring state's previous values. And we're going to keep doing this over and over again for each iteration, and the values get more accurate because more information goes through this entire graph. So, for example, we're gonna start solving this. So, in our first iteration, where is it? So we'll start with rotting. Oh, let me connect this line real quick. Our reward is -1 plus our discount, which is a half, times a probability 0.8 that we're going to stay rotting. And remember previously I said that when we start, we set everything to 0. Actually, let me just write that out. So 0 of rotting is 0, which is equal to V0 of class equal to V0 of discussion to V0 of passing. Let's go this way now. 0 of drinking equal to V0 of sleep. So now we get, it's going to be V0 of rot plus the other way we can get here, or 0.2 V0 of, let's call this day drink. This is equal to the first iteration. So now we're gonna have, next one is class. And so if we keep following this, for the first iteration, we're gonna reach the exact amount of rewards. So we're gonna have V1 of class equal to the same thing, which is gonna be class is -2, 1/2 times 0.6 of 0 plus 0.4 of 0 is equal to -2. So we're going to keep doing this for everything. So in our V1, we're going to get these values right here. Let's ignore that. I don't want to confuse. I just don't want to write all of it out again. We're going to get these values again. And so now we're going to go on to our second iteration. So in the first iteration, like for example, pass the class is going to have a value of 10 because it has an immediate reward. And go to discussion is going to look bad because it doesn't know yet that passive class is nearby. So even though like passive class is a reward of 10, this one's -2, and if we were to go to a discussion, we could easily just go to pass the class. Same thing with day drinking. This is just an immediate way we can get to our final goal. But at this iteration of the equation, we don't know that yet. So let's do the second iteration. Can I add a, there we go, insert a blank page. Let's go to V2. So now that we know that first we start with 0, blank slate, don't know anything. First iteration, now we know what all the rewards are. So now on the second iteration of rot, we have the actual reward, -1, plus again the discount. Now it's going to be 0.8 times, remember here we had the 0th iteration of rot, now we're going to have the first iteration of it. So this one's going to be -1, just like we have here, plus 0.2, that's here going to day drinking. V0 of day drinking would be whatever that, whatever V0 of day drink is. Oh, that should not be 1. There's 1, never mind. Which is going to be 1 here. This is going to be equal to -1 plus 0.4 plus 0.1.
When we say iterations, it's like, say we were to start at, say, rot, and then at rot in the 0th iteration, there's nothing that we know.
Yeah.
But then if we were to do now another iteration and say we moved from rot back to rot, we know that its value is -1. But if, say, we were to go to class, we know what its associated thing would be, which is -2.
Yeah.
And
so
on the first, and then if we were to do the second, then it would be whatever the second one is for those specific options that we could go to.
kind of. So when I say iteration here, it's like one round of updating every state's value. So it's not like in one it's like in one pass that the model looks at all of the states. So in one iteration, we go through and we look at all the states' value just as it is, all zeros, we don't know anything. That's the 0th one. First one we look, now we know what each one's like raw value is, the immediate reward. Now the second one we know a little bit more. Third one we know a little bit more. So each iteration is sort of like how the model is like getting the knowledge of the entire graph. It's like, remember we were talking about like the sequential decision making, like, oh, how do you know what time you're gonna go to the dining hall? This is like the model's equivalent of that. But each iteration, it's going through and like gaining more information, learning more about what the good and bad decisions are.
Okay,
And
so
you just,
adds iterations, it updates all the values so that, say, staying at rot would have, say, like a bit better because you can go to like day drink in the future.
yeah. So like at the very end, like what I'll say is that at the very end, after you have like an infinite amount of repetitions, like day drinking will have a value of 1.1. This going to discussion will have a value of 2.1 because as time goes on, this model is learning that if I go to discussion, I have an 80% chance of passing the class. If I day drink, I have a 30% chance of passing the class. But either way, these are the two states that are closest to passing the class. So these two are going to have the highest overall state values. These are the most valuable states because they're closest to passing the class. So as you make your decisions, your goal should be to pass the class. Remember I talked about Markov processes that if you're like, oh, I want at this time step to go here because this is my goal. What happens in between? In between, you want to go to discussion, and discussion is where you want to go. So the like third best one would be like I think like rotting. Rotting is like the third best one because then you can go to class. That's like the main ideas is that this is like sort of the equivalent of supervised learning.
Okay, so the model would do, say, an infinite number of these runs before it would actually end up traversing and actually making its decisions.
Yeah, yeah. It'll do this as much as it can until it converges to the same answers or gets some solution such that now it knows which state is the best, etc., etc.
Okay, and then
This is part of developing the policy.
okay,
Does that make sense?
yeah.
Yeah.
Okay. I think that if you want to solve it out, I'll go back to this at the end because we still have a couple more slides to get through, so I'll get back to this. The main idea is that it's recursive, right? Your iterations are based on your previous values because as you go on, you're looking at this entire graph over and over and over again. You're getting more knowledge about it. The way I think about it is it's like going to the dining hall. Your first day of class, you're gonna go at the worst time and you're gonna know this is not when to go. Your zeroth iteration was just coming to school, coming to UCI. You don't know anything about anything. You don't even know when the dining hall opens, right? That's why all of the rewards are zero for all the times you could go. Then you decide I'm going to go at 12:20 when everyone gets out of class and everyone's hungry, and you realize that is the worst time to go. So that gets like a lower reward. And then over time, you learn more and more. Your knowledge expands, and after like your entire first year, now you know when the best time is. Or even by the end of like fall quarter, you know what the best time is. But as time goes on, you learn more and more. That's sort of what this idea is. Make sense to everyone?
Makes sense.
Okay. So these are just like the same thing. I'm gonna go on to finding the best policy. So when it comes to finding the best policy, we touched upon it a little bit. Um, so the agent and the environment, they interact in cycles. At each step that we have, you get new information, and the agent uses that to improve its policy. Oh, sorry. For example, when we first had this example here, in our first iteration, we don't know anything. First, we learn a little bit more. But at each step, each iteration, we get more information and we can improve our decisions. Oh, I spelled functions wrong. So when it comes to this, there are two ways to make these actions. The first one is what we just talked about, the state value function. It's the expected total reward from starting at state S, which is basically saying, if I started off rotting, how good is it here? For example, if we started off going to discussion, there's an 80% probability that we'll go past this class. Right? That's a very high value state. Same with day drinking. There's a 30% chance that we'll go past the class. Now, versus if we end up at the state, go to class, we can end up going to discussion, but we might also end up day drinking, etc. And it's not as good of a state. So another type of function is called the action value function. This is the expected total reward taking an action A in state S. So this isn't just looking at where am I, it's how good a specific choice knowing that I'm at this place right now. This is better because it doesn't just take into account the state and the transition matrix, like the probabilities. It takes into account what you can do here. So how good is a choice? And the optimal policy picks actions with the highest Q value. So to find the optimal policy, you do something called Q learning. And sort of how we learned the different state values previously, we now can learn the Q values of all the state action pairs. So doing things like if you're at class, you have choices of either leaving class and going day drinking or leaving class and going to discussion. Those are the actions you can take. And your choice is that you want to pick the biggest Q value. And this is obviously very good for video games because in each one of these things in video games, you have a discrete set of actions that you can take. And you want to choose which action has the best return, which state you're going to get to next. The other one is policy-based, which is just directly parameterizing and optimizing your policy using gradient ascent so you can get to the highest expected reward. So this is not for things like, I have this set number of actions. It's sort of like as if you can imagine like a graph and like traversing it. Continuous actions are what this is useful for. And then the other thing I want to touch upon is exploration versus exploitations. As an agent, you want to balance trying new actions like exploration versus repeating the ones that you already know, which is exploitation. Too much of either is a bad policy. And so the example I would give of this is say that you're a baby. The baby knows how to crawl already. It can keep crawling forever. That's the action it already knows. That's just exploitation. You're exploiting the good policy you already know. But you must also balance trying something new, like walking, which might have a better reward later on. So it's important to explore and discover potentially better strategies in doing this, right? It's like you can if you keep exploring, so if you keep trying new things over and over and over again, you might risk wasting too much time and never getting a good reward. So a common method for exploring is doing something called epsilon greedy, which is a random action that you take with the probability of epsilon. So say you're a video game character and you're like exploring a certain environment. And in your game, you want to reach a certain goal. And now you can take the same policy action you've already have known, which is like say like using the same weapon over and over again, or you can try and use a new one, or try and explore a different path. Keeping on exploring over and over again might lead you to keep dying in this game. Versus if you just use the action you already knew, that wouldn't happen. But if you keep doing the best known action, sometimes you might take a longer time to finish the game. So oftentimes the best way to get around this is doing something called decaying epsilon over time. So by doing this, you take this value of epsilon here, saying we have this random action that happens with probability epsilon. If you keep decreasing it over time, the probability of doing something very random decreases. So as the policy gets better and better at learning, you want to trust the policy more and not do as much of this random action stuff. The way I think about it is this, like as the policy grows up, you want to just trust what you know rather than do something new. For example, you can be silly and like explore different things as a kid, but it gets harder and harder to do that as you get older. And you lean on things that you know more rather than trying things that are new. To charge my iPad real quick. 1 second. Oh, okay. Any questions? No questions?
Um, I do have a question. So
Mm-hmm.
back on like the MRPs and
Yeah.
how you calculate like different state values based on how like how close they are and like the probabilities to get to other state values, right? Um, do you like let's say the robot learns that it's not not the robot or the agent learns that it's a different probability than it originally thought. Is there a way to does it keep the current calculated state values and just try to improve them like from there? Or does it like start from the beginning with iterations?
So if the probability changes, you'd have to restart because one of the givens is that you have a fixed transition model or probability distribution to start with. So it's like partway through this exploration, your probability can't change. It's always going to be fixed. But let's say that you finished getting all the state values and then later on you change something in your transition model, then you have to recalculate all of the state values then.
Got it. Thank you.
Okay. Then let's go on to the coding example. Okay, so let me stop sharing here. Put this to the side. Wait, can everyone still hear me?
Yeah.
Let me go on to this. Give me 1 second, I just had to find it. I think it's on my SSD. Mm, sorry guys, trying to find it. Okay. So we're going to walk through how reinforcement learning works. Julian, could you, oh wait, never mind. Could you give me screen sharing power on this Ranakum? Actually, let me just leave from the other one.
Let me make this one a host for you.
Yeah. Okay, thank you. 1 second. Okay, let me share that. Okay, cool. And put this on the side. So we're going to walk through how reinforcement works, like from scratch. So remember, the main idea is that instead of like in supervised learning, where you sort of guide through telling what the programmer to do, we sort of just let this model figure out what it needs to do through trial and error. It tries things and then it knows whether it's good or bad through positive or negative rewards, and over time it improves. So we are going to use something that, like in 171, they like you go over. It's like the idea of like grid world. In it's like a grid, and the agent has to navigate from a starting cell to a goal and has to avoid pitfalls along the way. So our agent is this learner, this navigator, and the grid world is where it lives. It has a current position. It can go up, down, left, or right. +10 for the goal, -1 for each step, and -5 hits a wall. And our policy is that the strategy that the agent learns by doing this. And the Q table is where we learn each state action pair. So we talked about briefly. So this is the start, and this is where we have all these walls, and this is the goal. So here's our world. D is for where all the walls are. S is where we start. W is where we win. So the agent starts in the top left corner. It needs to reach our win at the bottom right. The dark cell is where it cannot go through. And the agent has 4 possible steps: up, down, left, or right. And after each action, the environment provides it with the reward, and it knows its next observation. So, for example, if it took a step this way, it would be -1. If it went down, it would be -5 because it hit a wall. And these penalties are on purpose because, well, I'm gonna ask you, why would we make penalties for each step -1?
That it doesn't just walk every single square so that we find the most optimal path.
Yeah, because we want the shortest path. We don't want to take the windiest route going back and forth till the goal. We want the shortest path there. And the wall penalty tells it to stop wasting moves. Don't hit the wall multiple times because that's not going to do anything useful. And so the algorithm that we're going to be using is called Q-learning. Q-learning is a model-free algorithm, and the core idea is that you have this thing called a Q table with 1 row per state and 1 column per action. And each cell stores the agent's estimate of how good the action is from that state. So sort of like how we had earlier in our state value functions, we had all the different values of how good each state is. This is basically something similar. At the start, the entire table is zeros, and the agent knows nothing. Then it starts exploring, and over time, it's able to figure out which states are the best and which ones are the worst. After each action, do you guys remember that equation where it was like V of S equals the current reward plus gamma, and then the summation of the probability of this state and the current state's transition times the value of the state earlier? You remember that equation? We kind of talked about it.
Yes.
Yeah.
Yes. After each action, we use that exact equation, and the new estimate of the reward is received plus the discounted and the reward it expects from the next state, and we put that into the Q table. And so there are 2 things that control this. And I want to ask you guys, what do you think is two things that controls how often we update the Q table? Oh wait, you guys can see.
Learning rate and discount rate.
Yep, the learning rate and the discount factor are the 2 things that controls everything. The learning rate is how fast we update the Q table, and the discount factor is how much we care about the future versus the now. And like I said earlier, what we care about is the highest possible Q value. And then once again, there are 2 main things. There's exploration and there's exploitation. And we talked a little bit about this, about the epsilon greedy policy, where in the beginning, we take a random action. And as time goes on, the probability slowly decreases, and we begin to taking the best known action instead. So this is sort of how our Q-learning agent works. We have the states, the actions, learning rate, discount factor, how often it explores, and then the decay rate. All of that we just set here. We choose an action, apply the Bellman equation, which is that summation thing, update the table at the rate alpha, decay the epsilon, and go on. Let's go on to this. So now we have our Q table shape, and now we're going to train it. So we're basically going to train this in 2000 episodes. And what this is basically showing is that at each one of the episodes, what's the amount of reward that we got, and like over time, how that's changing. So at first, it's a very negative reward, right? The agent doesn't know what it's doing. Remember how when we first saw the state value equation, we saw that the highest reward was day drinking, even though that only had a 30% probability of passing the class, versus going to discussion had 80%?
Mhm.
In the same way, right now the agent doesn't know what it's doing. It is just wandering around. It is not going to have a very high reward. But over time, it gets better and better. The reward starts increasing. The amount of steps start decreasing, and it becomes more successful. So on the top left, this is the total reward per episode, right? We can see that the line is raising and there's a sharp increase in total reward because very quickly it's able to learn where the walls are, which have the most negative reward. And you can also see here too that it quickly decreases its steps because it knows within the first iteration where the walls are, what to avoid. The top right shows the steps it uses to reach the goal. You can see here it drops very sharply. The bottom left is just the exploration rate, bottom right is the success rate, and it climbs to nearly 100% and just stays there because the agent is able to solve the maze. So let's look at the Q table. So on the left, you can see the policy that it learned. So an arrow in each cell shows the direction that it's going in. You follow the arrows, you can see where it's going, and on the right is a heat map of the maximum Q values per state. So the really bright states are the ones with really high values, and the closer you get to the goal, the higher it gets. This makes sense, and we saw this with the state value thing we did in the slides too, that the two states closest to the goal have the highest state values, and the farther out you get, the smaller that they get. Rotting and going to class had some of the lowest ones in our previous example. We just made the walls double because we never go there. So now, like, we want to make our improvements more concrete, right? We ran a bunch of these episodes, we saw how it went, but like in the beginning as well, it doesn't do that well. So a random agent that doesn't know anything has a very bad reward, but after Q learning, you can see that the reward got a lot better. It has significantly less steps, and it has figured out the optimal path. The agent is able to solve it like really well with a lot less steps and a lot higher reward than the random one does. Now, this is basically just to show you guys that, like, here, let's take a look at the code itself. That Q learning is the best way to sort of go about these like video gamey type of reinforcement learning things, because this is a way that really highlights a way to figure out the goal relative to like just a small amount of actions you can take. When things aren't continuous, it's easier to perform better for a model because there's less possibilities. Does anyone have any questions? Anything anyone want to try out with the code?
Makes sense.
Yeah, makes sense.
Okay then. I hope you guys were able to learn. Does anyone have any other questions?
How does it like change when like if it is like when the probabilities are like unknown or it figures out the probabilities as it goes, how does that like change and affect it in I assume like more complicated models of Markov chains or like
So, like for problems that have like a lot of different states and a lot of more probabilities.
no, I mean like if you had this is probably like a whole other lecture now that I think about it. But if you had um like the robot standing up, right? It doesn't know what the percentage of it taking one action has of getting it up. So does it still use the data from the beginning, or does that like decrease as it uses it, or is it like a cutoff point where it doesn't remember anything from 10 minutes ago and it just trains on the last 10 minutes? Or
So for the Bellman equation, it only uses what it knows from the just the previous iteration, nothing before that. Only what the states were valued at right before it. Nothing else before it. That's it.
got
Is that what you're asking?
um not really, but I'm kind of realizing as I'm speaking it out that it's a more complicated framework than and it's probably just a more complicated equation.
Okay, okay. If you want to see any lectures on something of like taking reinforcement learning to more complicated or more like further examples of it, then put in like the workshops channel on the Discord and then we'll do something on it in the future.
Okay.
Any other questions or things you guys want to see workshops on like in next quarter?
I guess neural networks would be cool.
Yeah,
Okay, neural networks.
neural networks.
Okay, so far, and I want to know your guys' thoughts on this because there's a lot of question marks on things to do projects on and like also workshops. So far, what I'm planning is introduction to LLMs, a computer vision one on CNNs, motion tracking, and then 6DoF spacecraft simulations. So you guys want neural networks?
Yeah, neural networks would be good. Um,
Ooh, transformers.
Transformers, okay.
That's good for the like introduction to LLMs.
Okay, I'll definitely have that in there. Any other ideas?
I don't know what type of machine learning this is, but whatever it's well probably a branch of the image one, but whatever like when someone has like a model that like recognizes a hand and like you have a hand in front of a camera and it has those different things. What like specifically does that use and like
Probably.
Okay, yeah, definitely. That would be really cool. Let's do that.
But instead of computer vision and also like pattern recognition.
So you said computer vision and pattern recognition?
Yeah, that's like the main stuff. Because computer vision actually, because if it's with a camera, at least you would need that computer vision, but then you have to add some elements of pattern recognition to know like, okay, these color blobs generally mean a hand, and then you plot out the most likely spots.
Okay, yeah, we should definitely do that. I'm trying to plan that for next quarter to do like a joint thing with projects. So we could do that as one of the projects and workshops joint things. Doing something with like computer vision and pattern recognition. That would be neat. Okay, that's everything that I have. I hope you guys learned some stuff about reinforcement learning, and if you're ever gonna make a project, use Q learning. It's good.
Yeah. All right. Thank you.
Thank you,
so much.
Freya. And I recorded this, by the way, if y'all want to ever look back on it. I'll post it on our YouTube pretty soon.
Okay, goodbye.
All right. Have a good rest of your day, guys. Bye. Yeah, this is gonna be the last one of this quarter, so bye.